Okay, this is tutorial 7. Just going to go through it real quick. Let me share my screen. You should be seeing the tutorial handout. Actually, it wasn't a handout, it's in the published book. And in this tutorial, we're going to look at the conservation of momentum in one dimension. And we start by looking at collisions here. We have two collisions. In both cases, we have a glider A on a frictionless track, and A collides with another glider. In the first case, it's M, and in the second case, it's N. And we're told that the two gliders, M and N, have the same mass, but that glider A is 1/5 the mass of the other two. And we notice that in the first experiment, glider A comes in and bounces off, comes in to the right and bounces to the left. In the second experiment, A comes in and stops. And we are asked a question about gliders M and N. What is it that makes these two experiments different? If they have the same mass and they're both on frictionless tracks, why would one cause A to bounce and the other one not? And the difference is that they could M and N could have different surfaces. I mean, N could have, I don't know, honey spread on it, or peanut butter for that matter. It could have been something that was made of a different material, like rubber instead of steel. Whatever it is, we observe these results here. Now, if we draw free body diagrams for glider A and glider M, in both cases, I've got a weight down and a normal by the track up. But for M, this should be 5 times longer. And this as well would be 5 times longer. And then I have this contact force, this normal force by M on A, and a contact force, a normal force by A on M. And those, of course, are equal to each other in magnitude, opposite in direction. So while the gliders are in contact, how does the net force on glider A compare to the net force on glider M? Discuss both magnitude and direction. Well, the upward forces cancel the downward forces, so the net forces are just these normal forces to the left and right. And so that means that the net force on A is equal to the net force on M in magnitude, but opposite in direction. That's what that minus sign means. And how, if at all, would this comparison differ if you had chosen a different instant while the gliders are still in contact? Not at all. Newton's third law applies. Oh, I'm sorry. Okay, I wasn't paying attention. Okay, I'll go back. So these are the free body diagrams. I've got the track pushing up, weight down on both of these. And then I have these contact forces here and here, and they are equal to each other by third law. And so the net force is just this contact force on A, and the net force on M is just this contact force from A. And so you see that the two net forces have to be equal to each other in magnitude, but opposite in direction. And that's what that minus sign means. And how would this comparison differ if I had chosen a different instant of time? The contact force between the two gliders, if I plot that as a function of time, is going to ramp up to some peak value and then go back down to zero as these two surfaces interact with each other. But at any instant in time, A is going to push on M just as hard as M pushes on A. Okay. If I consider the small time interval while the gliders are still in contact, how does the product F net of A times delta T compared to the product F net on M delta T? Well, if the net forces are equal and opposite, multiplying it by the same number, namely delta T zero, they're still going to be equal and opposite. So that means that the net on A times this time of interaction is going to be the net on M times that same time, again with the minus sign indicating that it's in the opposite direction. Now, if I start with this equation, F net is equal to M A, where A is delta V over delta T. If I multiply both sides of that equation by delta T, I see that it cancels out on this side. And so that means that F net times delta T is just equal to the mass times the change in velocity. And that's the change in momentum in situations where mass stays constant. And that's those are the only situations that we're going to look at. So if I want to compare the change in momentum for gliders A and M, I know that the change in momentum for A is just going to be F net delta T. That's what we just found right here on A. And we set up here that that's going to be minus F net on M delta T. And that's going to be minus the change in momentum of M. So what I end up with is that the change in momentum for A has to be the same as the change in momentum for M, but with a minus sign. Now, the consequence of this is that the change in momentum for the combined system of A and M has to add up to 0. And that's what we found in tutorial. Now let's look at those two experiments. In experiment 1, A had a certain initial momentum that was to the right. And then it bounced back to the left. And the change in momentum is what I have to add to this initial momentum to the right to get this final momentum to the left. I put these tail to tail to find a change, and that's going to be this vector here. I need a change in momentum vector that there's a plus sign right there. I have to take this initial momentum and bring it all the way back to 0 and out the other side. So that has to be a big change. In the second experiment, A started with exactly the same initial momentum, but after the collision, it was stopped. And so the change in momentum in that case was just what was needed to bring the initial momentum down to 0. So that means that the change in momentum of A for experiment 1 is greater than the change in momentum of A for experiment 2. Okay. What about the change in momentum of glider M in experiment 1 compared to that of N in experiment 2? Well, we learned up here that whatever change A has to the left, the thing it collides with has the exact same size change to the right. And so if A has a bigger change in momentum in the first experiment, that means that the change in momentum for M in that first experiment is going to be greater than the change in momentum of N in that second experiment. Okay. And since the mass of M, oh, that's unfortunate. Since the mass of M is the same as the mass of N, saying that they have a greater change in momentum in the first experiment says that the change in velocity for M must be greater than the change in velocity for N. And since both M and N started from rest, that means the final speed of M must be greater than the final speed of M. Again, by speed, I mean the magnitude of the velocity, but they're both going to the right, so that's kind of superfluous. Now, student 2, we're not going to call it student 1, but student 2 says, in experiment 2, glider A transfers all of its momentum to glider N, whereas in experiment 1, A still has some momentum left. So M does not get as much. Therefore, N has the greater final speed than M. Now, clearly, we disagree with this statement. And the thing that's wrong is that momentum is a vector. And if the final vector is in a different direction than the initial vector, the change can be greater than the initial. And this is true in real life. I mean, student 2 here is saying you can't lose more than everything you have. Well, anyone with credit cards knows that that's not true. I mean, you can, lose more than everything you've got and be in debt. And that's the case with vectors. They can go the other way. So now we're going to apply these principles to a couple of collisions. We're going to start with two gliders, C and D, that are free to move on this frictionless track. And C initially is coming into the right and collides with a stationary glider D. And we're asked to draw free body diagrams for C, D, and the system that is made up of both C and D. So for C, I have a weight force down, a normal by the track up, and this collision force by D on C. For D, I have a weight force down and a normal force by the track, and this collision force of C on D, and those are third law companions. And when I look at the system, the combined system of C and D, I would have the total weight of C and D. We call that the system. And I would have the normal force by the track on the system. Which forces in your free body diagrams for C and D do not have corresponding forces on the free body diagram for the system? And that would be the normal force by D on C and the normal force by C on D. And those are internal forces. And third law pair. And so they are not on my free body diagram for the system. The momentum of a system containing multiple objects can be defined to be the vector sum of the momentum of the constituent objects. Use this definition to write an expression for the change in momentum of system S in terms of the change in momentum of glider C and D. So if the change in momentum of the system is equal to the vector sum of the change in momentum of C plus the change in momentum of D, well, we know that when two things collide, the change in momentum of one of them has to be equal to the change in momentum of the other one, but in the opposite direction. So when I add these two together, that's going to give me 0. And so the system has momentum that is conserved. So momentum conserved for the system. Does the momentum of each of the following change during the collision? Yes. Okay, we know that C rebounds. And D, yes. D takes off to the right. System S, momentum is conserved because the net force on S times the time is 0. Are your answers consistent with your free body diagrams and the direction of the net force in each case? Yes. How, if at all, would your answer about the change in momentum of system S differ if glider D were replaced by a much more massive glider? We were never told what the mass of D was, and so this is not at all. Now we repeat this experiment, but this time we fix D in place on the track by supergluing it in place. And so we draw free body diagrams for C and D and the system. And I have, again, weight acting downward and the normal by the track upward on both of these, C and D. And then I have this contact force, the normal force by D on C, and by third law, equal and opposite force by C on D. And because D is fixed in place, I know that it has no acceleration. And so this diagram for D must be balanced. So there must be some kind of force here. We can call it maybe a static friction force by the track on D. And that kind of depends on how you fix that in place. If you put glue down, that would be a friction force. If you drove a pin through it like you had a butterfly collection, then that might be a normal force of the pin. But somehow we have to keep that object from moving, and the diagram for D has to scream balance. So now if I draw my free body diagram for S, I have this combined weight, and I have this combined upward force by the track. The third law companion forces, the internal forces, are not on a free body diagram for the system, but I still need this friction force, or however you labeled it, by the track on S. And the fact that glider D is fixed in place is reflected by the fact that this friction force has to equal the push by C on D by second law. And you always have to qualify your use of the second law with acceleration 0 in this case. Did the momentum of each of the following change? For C, it was yes. C rebounds. D, it's no. It's fixed in place. And system S, yes. The net force on S times delta T is not 0 anymore. So consider the two experiments described above. When the momentum of an object or system of objects did not change, were external forces exerted on the object or system? Well, yes. I mean, we had normal by the track on the system, and that in the first experiment, and we had normal by the track on D in the well, in this case, we had all sorts of external forces. So these were exerted. But was there a net force? That's a no. Okay. When F net equals 0, then the change in momentum was 0. When the momentum of an object or system of objects does not change with time, the momentum of the object or system is said to be conserved. On the basis of your results above, describe the circumstances under which the momentum of an object or system of objects is conserved. Okay, so when there is no net force, then P is conserved. Two students discuss the second experiment in which glider D is fixed in place. Student 1, when one object hits another, the momentum of the system is always conserved. No. We found that the change in momentum of the system, which was change in momentum of C plus change in momentum of D, this was 0, but this was not 0. And so this was not 0. Student 2 says, that's right, the momentum of glider C is the same before and after the collision. No. Momentum of C is a vector. The momentum of C initially was to the right, and the momentum of C finally was to the left. Not the same. Okay, that is the end of the tutorial. I will get this posted as soon as I can. Stop the recording.